first topic in our little section on quantum physics is just going to be looking at photons. We just need to make sure that we know what photons are and how we can calculate how much energy they have. So first of all, we'll start with the definition of a photon. Well, a photon is just a quantum or a quanta of light energy. That just means it's the smallest packet, so you can't divide a photon up in half. So you can't take a photon and split it into two smaller photons. It's indivisible, basically, and that's what we mean by quantum. And if we want to find how much energy each photon has got, we can calculate it using this equation. So E equals hf, where h is the Planck constant, which you can find in your data book. That's 6.63 times 10 to the minus 34 joule seconds. And then the frequency is just what the f is standing for. So the amount of energy a photon is going to have is going to depend on its frequency. Now, we do also know that f is equal to wave speed over the wavelength. So I could substitute that into the equation and come out with E equals hc over lambda. So that means that I can quickly calculate the energy of a photon if I know its frequency or its wavelength. I don't have to convert from one to the other. Now, when we're talking about photons, we're often talking about how much energy they have, and the energy, if we do it in joules, is always going to be a really, really tiny number. So just like with electricity, when we talk about kilowatt hours as being a large amount of energy that's more useful for household electricity, we have electron volts, which is a small amount of energy, which is more useful for when we're talking about photons and sort of quantum effects. So the unit that we have is the electron volt. And 1 electron volt is the energy transferred when an electron travels through a potential difference of 1 volt. So that's 1 electron volt equals 1.6 times 10 to the minus 19 joules. So if you remember from your electricity topic, you have an equation that is W equals QV. So the amount of energy equals the charge times the voltage. That's where this comes from. That's what this is saying. And it's just the definition of the volt just rearranged, basically. So 1 electron volt is 1.6 times 10 to the minus 19 joules. And you have to be able to convert between joules and electron volts. So to go from electron volts to joules, you multiply by 1.6 times 10 to the minus 19. And to convert from joules to electron volts, you divide by 1.6 times 10 to the minus 19. Right then, in the equation for the energy of a photon, I talked about this constant called the Planck constant, and I just gave you the number. But it is actually possible to do an experiment in the lab, which we will do, to come up with an estimate for the Planck's constant, and we can do it using LEDs. And that's because LEDs have got a very useful property. When they just begin to glow, the energy of a single electron that's passing through that LED is transferring all of its energy to a single photon. So if I can calculate how much energy each electron has, I can calculate exactly how much energy each photon has. And if I put those two things equal to each other, so I use W equals QV, and I use E equals hc over lambda, put those two equal to each other, I get this equation. The charge on an electron times the voltage is equal to hc over lambda. Now, what I would like you to do before next session is have a little think about how you might carry out this practical so that we could get a good estimate for the value of the Planck's constant. Remembering that when we do practicals to find a value, we are probably going to want to do more than one version of it, so we might want to do some repeats where we change a value of something, and we will probably want to draw a graph and get a gradient. So I want you to start thinking about how you might carry that out, because that's basically an exam question in and of itself right there. Okay, so I will see you in class, and if you have any questions, just ask when you see me.